Well, thank you, Jason. I appreciate the introduction. Um, and yeah, as he said, my name is Brian Zimmerman. I'm a climate scientist now at Salient Predictions, and I'm going to give a talk here, kind of focusing on looking towards better data practices in S2S forecasting and try to give you all a perspective from a private company that's in industry. So just to kind of give a brief overview of everything, the fundamental problem that we face is that in an increasingly volatile climate, S2S forecasts are now drawing more interest. And the uncertain nature of S2S forecasting really requires attention to detail. And this is both in machine learning, artificial intelligence data practices, but as Jason indicated, my passion thinking about probabilistic forecast communication and decision making and how to communicate uncertainty and probabilistic forecasts in general. Our approach at Salient is data driven. This enables rapid experimentation. I think this is one of the benefits of being in industry. And our philosophy then centers around results-based transparency. And I'll spend some time talking about that later in this talk. Another advantage or something that I really like about working at Salient is that we have a really diverse team. So that includes climate scientists, machine learning engineers, data scientists, and that's just the technical team, not to forget about our product development people, our biz dev people, and people who are out there engaging with clients. And so this whole team really enables robust model development because we have a lot of different perspectives. Client needs drive most of the things that we do, and I'll touch on that a little bit. And then finally kind of end with this concept about education on proper S2S utilization is important and oftentimes overlooked. I'll kind of skip over this slide since Jason gave me such a nice introduction. The one thing I want to point out is that all the way back in my first graduate program, working with Paul Block, Dan Weimont, and the Water Resource Engineering program, I was working on a project that involved utilizing probabilistic season ahead forecasts to inform reservoir decision making and management for surface reservoirs in the Western United States. And so I've kind of been involved in this space and thinking about these problems for a long time. And it's really exciting. It's been exciting for me to come to Salient and be able to engage with clients and end users to kind of talk more about those problems and try to bring all of these things in line. So just to overview and a background, who are our customers? S2S forecasts, seasonal to sub-seasonal forecasts, who needs them? The energy sector is one of our main clients at this point. We have a lot of active pilots going, and they're interested in things like load forecasting, demand forecasting, renewable production, and then trading and hedging to manage the load forecast, the uncertain nature of the load forecast, the demand forecast, and the renewable production. We also have worked and are working with insurance companies, hoping to better price and underwrite products and provide value-added tools to reduce claims. That's an active pilot that we've had going for some time. And then also in the agriculture space, we've worked with clients like AB InBev to think about global supply chain sourcing, optimizing planting decisions, harvest management, and things along those lines. And so these are all sectors that have exposure to significant weather and climate risk, and also who make long-term planning decisions and would like to have some type of advanced information to assist them in making those decisions. So a little bit about our product and the solution that we provide. The Salient Blend Forecast is our core product. It's a global product. It's calibrated to be reliable. It's probabilistic in nature. We have four main core variables that we forecast: temperature, precipitation, wind speed, and solar insolation. Going back to our client usage, right? All of those things are important for energy production, agriculture, also insurance, damage claims, those types of things. We really focus on the 2 to 52 week time scale. That's what we refer to as the S2S forecasts. We offer weekly forecasts, so of weekly averages. I'm talking about the temporal averaging scheme. Weekly forecasts out to 5 weeks, monthly out to 3 months, and quarterly out to a year. We increase that temporal averaging the farther we go out in order to try and maintain signal within the noise, and I'm sure many of you are familiar with that problem. It's on a global quarter-degree grid. We offer some point-based debiasing to weather stations. We have other pieces of the product. We can think about daily downscaling, things like that, but this is kind of the core of the product. This is just an image from our web viewer, and so the clients have access to this. But most importantly, I think we offer a in-depth API access to basically every piece of our forecast. And so you can get a lot more data out of the API than you can just by looking at the viewer, but it's good to have both of those things, and different clients prefer to ingest the data in different ways. It's just important to note that with the API, you can get much more granular and specific location data, upload shape files, pull all these different things together. And so that's a really important piece of being an industry player, is that we need to have easy access to our data for our clients. But I kind of want to now shift. That's just a little bit of background on the company, what we're doing, set the stage. What I really want to talk about in this talk and with you all, and get some of your perspectives at the end, are our data practices here at Salient. And so this is something that we think a lot about. And so I want to talk about, in order to, the first thing you need to think about having a good data practice is, what are the attributes of the forecast that are important in this point. And so in order to produce honest S2S forecasts and not overconfident forecasts, to correctly quantify the uncertainty, it requires a lot of attention to detail. So some of those forecast attributes that we think are really important are, first, the probabilistic nature of these forecasts. All of our machine learning, our artificial intelligence models operate in quantile space. We do pull in the global dynamical models that are available, and those come in ensemble space, also probabilistic. This allows us to quantify uncertainty. It also allows us to make more specific forecasts. So say someone is particularly interested in the chances of being below freezing for an extended period of time. That is a question that you can answer with a probabilistic forecast that you can't with a deterministic one. The second thing that's really important, I think, is proper scores. And so we think when you're utilizing probabilistic forecasts, you need to also utilize proper scoring metrics. The continuous rank probability score, the CRPS, is one that we focus a lot on, although we do have a full suite of deterministic and probabilistic scores. It's good for fair evaluation of these types of forecasts. We also produce skill scores, which allow easy comparison among all the different model types that we have. And that's broken out by time scale, season, and lead time, so that we can focus our efforts on, different users are interested in different aspects of the forecast when it comes to timing and lead. The final thing that we think is really important is the concept of reliability. All of our models are calibrated, and we make the reliability diagrams available in the typical climate conception of the above-below tercile categorical forecasts. And so that allows, we can put the salient blend, and as we do with the skill scores, you can compare it to any of the other models and see the frequency of forecasts at certain probability levels, and then also the actual reliability line of those tercile forecasts. So next in our data practices, and maybe of particular interest here, is kind of our machine learning stack. And so the main takeaway here is that the Salient blend, our forecast, it has everything that we've got kind of built into it. And this goes along with our results-based transparency type philosophy. So in our system, it's a set of modular components, and we really think of everything as a model. And so I've got the Salient blend, which is the final output at the top there. And if we come down to this bottom layer, you can see that what we would normally think of as a forecast model, those kind of are stacked along the bottom and are foundational to the system, right? So we have artificial intelligence and deep learning models, the MLP type architectures, CNN architectures. Essentially, we could build in any type of deep learning architecture that we would like there. We also produce a set of statistical models, so climate index-based models, a linear inverse model, although you could argue that's not a simple statistical model, but it's not the same as a deep learning one either. and also just Monte Carlo and stochastic type models for experimentation. We pull in the global dynamical models, both GEFS and ECMWF, and then we also build different types of climatology models. And so, kind of alluding to the conversation Matt and I were having at the beginning of this, if some of you were trickling in and overheard that, climatology can be calculated with trend, without trend, over 10 years, 20 years, 5 years. What do you want to use? And so we also think of that as a model. The next layer on here is a set of calibration models. And so we want to be able to calibrate everything that we're putting into the blend. We think of the climatological models as reliable by definition. When it comes to the dynamical models, we essentially, because they're ensemble based and we want to convert them to quantile space, we use an ensemble statistics calibrator. It's analogous to the EMOS methods that were popularized out of the University of Washington, earlier in the, well, I guess earlier, 20 years ago, 30 years ago now, maybe. We've also built quantile function calibrators that can then take our statistical models, which are created in quantile space, and calibrate them. For the AI and deep learning models, we take a slightly different approach where we encourage reliability via the training loss function. And that kind of points back to why utilizing proper scoring metrics is important. The final layer we have here is essentially the blending layer, but every blender is also a type of model. So we could do simple skill-weighted blending, we can do flexible quantile-based blending. If we wanted to use neural networks to blend the models together, we could do that. And so we kind of so we stack all of these layers together eventually to get the Salient blend forecast out. Now, the most important piece of this data practice, and what I think makes the prior slide and our ML stack valid, is our approach to cross-validation. And so this also has to do with our results-based transparency and why we're confident in our results. And really, it just comes down to proper cross-validation for us. So I can't emphasize this enough. It's really critical. I'll show a little example later, but data leakage is a really big problem, and it's even big for simple things like climatology. We discovered that the effects on the skill of climatological forecasts can be in the realm of 10% if you don't cross-validate them properly, and that was a bit of a surprise to us. So importantly, we cross-validate everything with the same scheme. So climatology, statistical models, AI models, calibration models, everything. The figure on the right is our hacky cross-validation scheme image, but you get the idea that we produce hindcasts from 1980 onward. We do use era 5 data back to 1950 when we're training our statistical and machine learning models, but we don't actually do any scoring until 1980 and beyond. And so it's a pretty simple 5-fold cross-validation scheme that you can see there. And then the final fold forecast, there's fold 7 forecast for our test set. And then when we operate in real time, that final fold on top, fold 8, we're training on all of the data. But when we report our skill scores, we're using this scheme. And that's because we value the full transparency of it. And I think our scoring process is really well documented. So that's a piece of transparency when it comes to clients. We provide all these hindcasts through our API so that clients can run their own analyses. We also provide Jupyter notebooks with tutorials on how to use the API, how to access the hindcasts, how to score them, etc. Not that everyone is going to use those, but we want others to be able to analyze and validate our data. We don't want that aspect of it to be a black box. And then communicating that we're properly cross-validating the system, I think then builds the trust to be able to believe in the metrics that you're calculating or the validation that you're doing. So some people might then ask, what about the black box nature of this approach, especially when it comes to our deep learning models? We don't currently utilize any explainable AI techniques. It turns out while I do believe that's really important for academic studies and this idea of understanding, trying to understand the fundamental processes at play, it turns out it's not that important for industry clients. Most of them probably are not even going to know what a layer-wise relevance propagation map is, much less ask for one. What we do find is that, for instance, some energy clients especially, or people who are used to looking at these forecasts or maybe have been using ECMWF extended range for some time, their idea of explainability is seeing, to a temperature anomaly forecast, they want to see a comparable 500 millibar geopotential height forecast because they want to see the physical representation between the two correspond, and that's how they build trust in the forecast. And so it's just a different approach to thinking about these XAI techniques. We would build it in if clients asked, but that's not something that's happened yet. Another thing that we have noticed is that data-hungry methods like these that we're using tend to be really easy to overfit. We see this really often in machine learning applications, especially when machine learning is applied naively in non-machine learning fields. This kind of goes back to the point I was talking about having a diverse scientific and engineering team where we have machine learning engineers that can communicate to someone like me who thinks about climate science why the way I'm approaching something from a machine learning perspective isn't actually valid or doesn't make sense. So things like that allow us to really believe in our cross-validation scheme and the blender. That's kind of our focus. And we construct a lot of models, as many as we'd like, and combine them in an optimal way for the best result. And then I just kind of wanted to include this at the end when we're talking about explainable AI. It was interesting this year, the word hallucinate and the new definition related to AI is the Cambridge Dictionary word of the year. And so I asked ChatGPT to draw me a simple and concise graphic explaining cross-validation. And turns out it seems to be really into the idea of cross-validating. So I think we're going to try that next. Okay, all jokes aside, one of the other things that I had mentioned is this concept of our machine learning architecture allowing for really rapid experimentation. We believe that this enhances model quality. And so at Salient, scientific experimentation and debate is highly encouraged. And while it's results focused, it is also process based, right? And so we have a lot of discussion amongst the team. We design experiments together, run them, and then go over the results together. As I said, the machine learning architecture allows for the rapid experimentation. We don't need supercomputers. We do need person hours to set up the experiments, analyze the results, etc. But we really believe that robust debate creates robust models. And so I know I've made this point a couple of times now, but again, having this variety of background among our team members allows us to approach these problems and this experimentation from a bunch of different angles, get a bunch of different perspectives, and apply the best practices from each one of those disciplines. And so we think that that helps make that makes our modeling process much more robust. And then finally, the rigorous cross-validation framework plus a comprehensive set of evaluation metrics, that gives us confidence. So we evaluate deterministic metrics, probabilistic metrics, categorical metrics, all the ones you're familiar with, CRPS, MAE, Heidke, Breyer. We also create the skill scores for every metric and every model baseline. So we can look at, like I said, within our modular system, with everything being a model, we are able to then compare each individual model against another on all of these metrics. And the idea behind that is that if you see something great in one metric and it doesn't appear in a corresponding one, it kind of just like gives us that gut check and allows us to kind of, in a way, both qualitatively and quantitatively look through these skill maps, look through the different seasons, the regions, the leads, and the time scales, and really try to identify what is leading to the increased skill that we're seeing, or if it's just an artificial aberration, because those are not unlikely to happen again when you have these limited sample sizes and you're operating in this space. Excuse me, just one second. So just to kind of, I'm going to go through two quick case studies that we've done recently, just in the spirit of experimentation, just to kind of give you an idea of the things we think about, and also show that they are more results focused than fundamental process focused. But ideally, that's something, we do read and are heavily invested in the academic world, and we consume academic literature, right, for these different ideas and to try and bring it all together. But from our perspective, right, in this case, the research question was, given that we provide forecasts at a 1/4 degree resolution, what's the optimal native spatial resolution to build machine learning models? So we build a bunch of models and generate hindcasts at a bunch of different resolutions, coarsen the fine models up, interpolate the coarse models down to all the resolutions, compare the output across regions, variables, and timescales. And then really this important piece of it is the discussion. We have a very active internal science Slack channel. I think for this particular case study, I think there was something like 34 replies in the thread. But each of those was, half of them were nearly a paragraph, right? And so and the asynchronous nature of Slack allows us to really kind of engage in deep discussion about what we're seeing. We link to the files, we link to the outputs, we link to the images, and have this it's actually quite fun and enjoyable from my perspective. And then one of the other things we do is a monthly science review. So those of us on the science team once a month pull together just kind of the highlights of what we've been working on, experiments we've been running, things that we're thinking about, and make a presentation to the rest of the company to keep everybody in the loop of what's going on. The other one I wanted to share really quick was the case study that we did on the climatology data leakage, just because I had mentioned it before. And so we're wondering, what was the effect of removing data leakage by applying CV to a simple climatology model? And the rationale was that for any statistical model, it's unfair to test on the data used for training. And also, since we're communicating these skill scores, and we're so rigorously cross-validating our Salient blend and the calibration and all these other pieces, when we're comparing it to a climatology forecast, it should probably be fair. We also, like I said, we have clients that ask us about 5-year climatologies or 3-year climatologies, or that's what they're already using. And so we try to make a case why you should maybe incorporate more years. The brief results of that experiment are just kind of presented here on the right with the continuous rank probability skill score compared to our current non-CV trended CLIMO kind of going down. And it just shows that if you add cross-validation, the skill drops about 6%. If you detrend that, if you don't detrend that and cross-validate it, it drops down 8%. And then if you only use 5 years, it drops down to 15%. That's again likely because we're using a proper score. And so when you're only calculating a CLIMO on 5 years and cross-validating it, it's not actually sampling the variability appropriately. Now, I know this is just a very simple, quick overview of this type of thing, but the greater takeaway point is that we have the framework to be able to quickly analyze basically anything that we're interested in and then present results among the company and among the science team and discuss and move forward. So I have just a couple of slides left. That's the bulk of kind of this important data practices that I wanted to talk about and just kind of illuminate how we think about it as a company. Two other pieces though another piece that's really important to being in industry is client satisfaction. And so the API that I mentioned before, that really facilitates client use and uptake. Turns out that if you don't have a lot of experience, S2S information is quite difficult to use, and we do our best to make it easy. Clients need to be able to easily access and ingest this information. Our API allows for real-time workflows, which is a critical piece of being in a company in industry. And then our product officer is out there constantly integrating client feedback and requests into the product roadmap. The image that I'm sharing here is kind of a new API tool that's in development. We're about to release the MVP, which is the minimum viable product, I think next month sometime. But in this case, it's a risk API. And so we are able to quantify and set specifications and thresholds for different types of risk and assign them risk levels. And that allows us to customize the forecast to a particular client. And they can input, and we're happy to converse with them and decide what those inputs should be. But they can input the thresholds that they want to receive some type of alert level at. Whether it's a absolute probability of being over some value, or some divergent forecast compared to the dynamical models, or some X times risk compared to the climatological forecast, etc. And then they can be automatically alerted of those things. They can see it in the map. And I just bring that up to show that that's something that we are encouraged, I would say, to be flexible and alter our products and our processes for communicating this information based on client feedback. And then, of course, we have comprehensive help documentation. We publish some white papers about our methodologies, and that's all available within our help center. Talks about forecast and hindcast, the variables, reliability, what we think about all of this kind of stuff. And so we try to make this really accessible to our clients. The last piece I want to touch on is, again, like my personal interest is understanding how probabilistic forecasts can facilitate better decision making. And so this graphic, this was actually my AGU poster this year that I just came back from. And so it's not meant to be read or studied here. If you're interested, please feel free to email me. I'd be happy to send you a copy of it or discuss it offline. But the idea is, how do we use probabilistic forecasts to think about decision making and manage risk better? And it turns out that most people are not used to thinking about it in a rigorous way. And also people don't have a intuitive understanding of what probabilities actually mean. And I think kind of what this poster does, the idealized case study that I point out, goes through the concept of, if I'm just one actor with one realization through the world, what does using a probabilistic forecast look like? And I built a little model, and you can run it a bunch of times, and then you can start to answer questions like, what are the odds of being wrong 2 times in a row? What are the odds of being wrong 5 times in a row? And you could see some kind of industry where that difference in the likelihood of being wrong some number of times in a row might have a huge impact on the bottom line for a client, whether it's agriculture or insurance or anything along those lines. And so I kind of came up with this poster and these ideas to really just start engaging in discussion with people, and to start helping think about what risk in your capacity looks like. And so again, please feel free to email me if you'd like to talk further about anything along these lines. That's the bulk of my presentation. Here are some opportunities that I've kind of just thrown out there for future development and collaboration, or any kind of discussion topics that we might want to get into now. And that's basically just regarding how do you think about best practices, how these best practices might apply also to numerical weather prediction, the way that we apply them to machine learning and thinking about those, because those are also models and they have parameterizations, and how do we validate those things? I don't even really know the answer to that, but I think it's worth thinking about and talking about. One thing I think that's really interesting is this idea of a common framework for experimentation and validation. Google has kind of been getting at this. I don't know who else is familiar with WeatherBench 2, but that to me seems like a step in the right direction. How could we make something like that more concrete or more useful across both industry and academia? And that leads towards bridging the trust gap, and then thinking about, I think one interesting thing would be to talk about the interplay between best performing models versus this idea of gaining understanding of the fundamental climate processes, I think they can feed each other. And so I would be really interested to hear perspectives on that. And then, yeah, the last few are kind of self-explanatory, and I think I've been slightly over my time, but I really appreciate everyone's attention, and I think we have time for questions and discussion. And I'll just kind of open it up and leave it there.
Yeah, this was good to hear the how does the industry uses all these forecasts. I think a question that you sort of already touched, like how do you select which climate model to use? And yeah, one more question I have. You talked about S2S. I think the second question is 2 weeks to 52 weeks. So, what's your experience in terms of the skill, or how do you communicate like a 2 week skill that we expect it to be higher versus 52 weeks, or how does the client uses these skill score?
Yeah, thanks. So I'm going to go straight to the second question because the first one, I'm not sure if you meant climate models or our climatology models. But I think the second one is actually more interesting, right? How do we think about communicating the skill of those forecasts at the different lead times? Um, in our experience, right, the farther you go out, if you're properly calibrating a model, the farther you go out, the more your forecasts are going to look like climatology. And I think that's an important piece of calibrating and communicating that type of information because no one should have that much confidence in a forecast for something, 9 months from now. Um, However, the important piece of that, right, is that if you trust in your system, when you see probabilities that do deviate from climatology, you're able to take act like that is what even the community talks about as a forecast of opportunity. Uh, Now, how much of an opportunity then depends on who you are as a user, what your risk tolerances are, what types of costs, what the cost loss benefit decision that you have to make in using that kind of forecast. And so that's how I think about it and like to communicate those types of things.
Thank you.
Hey, Brian, I was just kind of curious, like how much human oversight is required in this process? Like how much is automated? And I don't know how much you can actually say. Because I'm just kind of curious, like what are you doing on a day-to-day basis?
Yeah, well, so the system, right, the framework is automated in a way where right, the cross-validation scheme is implemented almost as like the base modeling class within our modeling system. So and then in the end, right, we have scorers and score plotting mechanisms and all of these different pieces. So whenever we run an experiment and change a set of parameters, we have a set of metrics that are calculated, a set of plots that are made. Now, so that part is all automated. Uh, Looking at those plots and then discussing them among the team or trying to hypothesize about why making some parameter change led to something that we saw, that's still a very human oriented process. And like I said, I really feel lucky to be unsiloed in some sense, like working in the industry, because people just have, some of our machine learning engineers come from like an astrophysics background where they were doing Bayesian modeling or whatever. And so their perspective, they just see things that I wouldn't see because I've been looking at these same maps for 10 years and I'm over, like might be missing something easy or whatever. So there is still a big human element involved.